All right. Hi, everyone. Thanks for joining. So today we have a great pleasure of having Harita Dellaporta, who's going to present her work on robust Bayesian inference for simulator-based models via the MMD Posterior Bootstrap.
Cool. Hi, thanks, Antonin. Thanks to everyone who joined online and here. So yeah, this is the project I did during the first year of my PhD. So that was joint work with my supervisor Theo and Jeremiah Snowblatt and FX Briol, who are both from UCL Stats. So an outline before I begin. So I'm gonna talk to you a bit about motivation for our method. So what are simulator-based models and the problem setting we're considering. And also give you some background on robust likelihood for inference, Bayesian nonparametric learning, which is a framework where we based our method on. Then I'm going to talk to you through our method, some theoretical results, and a few applications at the end. Okay, so we're saying simulator-based models, so we're considering models for which independent sampling is possible. But we don't have an analytical form of the likelihood function, so we can't evaluate that exactly. We don't have the density essentially. And in a lot of cases, these models are quite complicated. So they come across a lot in natural sciences because they try to describe a real world phenomenon that usually is quite complex. So they give a rough approximation of what's going on, but they usually can't capture all the characteristics of the data generating process exactly. And for this reason, they are quite often misspecified. So we want to tackle these two main things, that we don't have a likelihood function, and we also think that it's quite likely that we are in a misspecified model case. So a bit more formally, we're going to consider a model family, a simulator-based model. So that is going to be indexed by some parameter theta. So we're still interested in Bayesian parametric inference. So don't let the non-parametric learning framework confuse you. I'll come to that. So we're interested in making inference about theta. And our model is defined through a simulator function. It's also called sometimes generator function, indexed by parameter theta, and a base measure u, which is usually something simple you can sum from, like a uniform or a normal. So in order to actually sample from this model, you have to sample from u and then map it through the generator. So that's how you obtain independent samples. And in terms of the model misspecification, so if we observe some data from the true data generating process, which we're going to know by P star. Essentially, what we don't want to assume is that P star is necessarily a member of the model family. So we don't want to assume that theta, there is some value of theta that will recover P star exactly. So that's an assumption often made in standard Bayesian statistics, and what we want is to not make this assumption and just try to find the model P theta that will best describe P star, even if it's misspecified. Okay, so of course there exists like robust likelihood for inference is quite a big literature. So a big class of methods that exist is approximate Bayesian computation. And I'm not going to go too much into these methods, just to have an idea of what else is out there. And there's also generalized Bayesian inference is something that's used quite a lot recently in the cases where we don't have a likelihood, because the main idea of this is that instead of using a likelihood function, we can use a generic loss function in our Bayesian updating. And this can both, alleviate the problem of not having a likelihood. So if I use a loss function that's not based on the density, I can use that in likelihood for inference. And also there's been some work recently that attempts to make this even more robust by choosing the loss function in a efficient way. Now, a few things about this method that we kind of try to avoid. So, of course, GBI is also connected with setting a weight for this loss function that affects posterior inference, and there's quite a big literature of how this should be set. And also, from a computational point of view, there's a lot of these methods are like inherently sequential a lot of times, so they use some complicated like sequential Monte Carlo or something like that. So that's also something we've kind of tried to like make something a bit more parallelizable. Something we've tried to tackle here. Okay, so that's just an idea of like alternative methods. I'm going to now go into the Bayesian nonparametric learning framework. So we're going to put aside the likelihood for inference bit for a second and focus on the model specification problem. So this is a framework introduced in a series of papers in 2018 and 2019. And the main idea is that in Bayesian inference, you would usually assume the model is true and set your uncertainty on the parameter of interest, so through a prior distribution. But what the authors suggest is that if I don't want to make this assumption, I can set my uncertainty directly on the data generating mechanism, which I don't know. And by doing that, I want to find a way to propagate uncertainty from the data generating process to the parameter of interest. And the first step to set uncertainty on the data generating process is to set a prior directly on that. So what they suggest is a Dirichlet process prior. So that's a prior distribution for P star, and it will be is centered around a prior centering measure F. So F will have the information of where the prior information about P star. So where I think maybe some expert knowledge or anything else that I believe about P star. And then alpha is a centering parameter, which will indicate the strength of my prior belief. So how much I think my prior is, how much I believe on my prior. And the nice thing about Dirichlet process is that it has a conjugate posterior. So for IID data, I know that my posterior will also be a Dirichlet process, and you can see here exactly the role of alpha, because the posterior will be centered around this base measure F prime, which will be a linear combination of my prior centering measure and the empirical measure from the data. So if I set alpha to 0, for example, it's like having a non-informative prior in the case where I really not sure about P star. So I have this, all I've done so far is essentially done Bayesian inference on P star directly. So I haven't included my model at all yet. And what I would like to do is use this posterior distribution of a P star to make some statements about theta, right? So what the authors say is that if I have a loss function on my data and theta, my target essentially would be the value of theta that will minimize the expected loss under P star. So this map here, theta star, which is indexed by the loss function L, says that if I knew P star, then my target will be exactly this minimizer of the expected loss. Right, so this start from the space of, sorry, this is a map from the space of P star to the space of theta. And this, of course, if we knew P star, then we're okay, we can validate that. But we don't know P star, so we have a whole posterior distribution of a P star. And so we need to find a way to propagate this uncertainty, get a posterior over theta. And what they say is that essentially this map, so we have a posterior measure and a map between P star and the theta spaces. So this defines a push forward measure so that we can obtain a posterior of theta. So if you're familiar with push forward measures, that's what mathematically a posterior on theta will be. It's just push forwarding the posterior measure through this map. If not, don't worry, because I will get back to it when I explain how to sample from this, and I think it will become a bit more clear. But essentially, they say that we have a non-parametric posterior of the data generating process, and we can push forward this posterior measure to the space of theta through the map that says minimize the expected loss under P star.
Can you just remind what P star is?
Sorry, P star is a true data generating mechanism. So that's where our observed data come from, and it's unknown. So the prior here, P, is a prior for P star. Okay, so now, so before I explain the sampling procedure, I want to get you through a bit into the method. So we have this framework that we would like to be suitable for simulator-based models. So we want both computationally to be something that doesn't require the likelihood function, and we also want to make it as robust as possible. So the idea is, what we proposed is that instead of minimizing an expected loss, we can use a distance-based loss. So we can minimize some distance between probability measures. So if we have any distance d, our target can be rewritten as the value of theta that minimizes the distance between the true data generating mechanism, P star, and the parametric model family, P theta. So that's what I want to get. So that's the target. That's where I would like my posterior for theta to concentrate. And the right-hand side of the map is essentially becomes a minimum distance estimator. We just, this minimization of expected loss, we kind of transform it into a minimum distance estimator. Which again, here will be indexed by d depending on the distance I choose. And the distance we proposed is the maximum mean discrepancy, which you probably guessed by the title of the paper. Sorry,
just a quick question. So what's the relation between these two optimization objectives on the previous slide? Like,
the expected loss.
Yes, and the one that you constructed.
Yeah, so it's just so instead of using a loss function directly on the data and the space of theta, we would just want to look at the parametric model family, so the measure P theta and P star directly. So it's just using a distance-based loss. It's a loss function, but it's defined for distance between probability measures. So it's just a specific special case, if you like, of a loss function here. Yeah. Okay. So maximum mean discrepancy. So if we use the maximum mean discrepancy, what we get is a minimum MMD estimator on our map, which were very thoroughly explored in a few papers. For example, this by Briol in 2019, and this one by Sarif Abdelatif and Alker in 2022, this paper actually worked on finite sample properties of MMD estimators, and we used quite a lot of the theoretical analysis to obtain our theoretical analysis. So it was quite useful in our work. Okay, so what is the MMD, first of all? So the MMD is an integral probability metric. So IPMs are defined for a specific class of functions, F, and essentially they look at the supremum of the difference of the expected value of functions in this class under each of the two probability measures. That's how they measure the distance between P and Q here, for example. And for different choices of F, you can have a different IPMs. And of course, you're not, depending on the choice of F, this may or may not be a metric for generic F. So for the special case of the MMD, F is a unit reproducing kernel Hilbert space. So these are defined through a kernel function. And the nice thing about mapping our class of functions into RKHS is the reducing property. So the fact that it allows functions to be written in terms of the kernel functions in the inner product of H makes actually computation of this supremum a bit easier. So from a computational side of view, if I now want to go back to my problem, so if I want to actually minimize an MMD between P and Q, for example, so this will be a supremum over an KHS with the norm of the functions upper bounded by 1. And this is well known that it attains this closed form for the squared MMD. And when I say closed form, I mean closed form in terms of the fact that you don't have to calculate this supremum anymore. But of course, you have still to estimate these double integrals. But these integrals now only depend on expectations of kernels. So they can be approximated through simulation, which is what makes them quite suitable for simulated based models, because all you need now is to be able to sample from your model. So there are quite a few estimators of the MMD. So U statistic is one that we used, which was introduced in this paper, and essentially, so it approximates these double integrals through sampling. So in our case, in going back to the MPL framework, our target now is the map theta star, which now without an index, I would assume that's using the MMD as a distance. And it will end up being the value of theta that will minimize the MMD between P star and the parametric model family. And in practice, it will minimize an estimator of the MMD. Now, apart from the computational side, the MMD was quite, as I said, it was explored in these two papers, and it was shown to have some really nice robustness guarantees on its own. So the nice thing about this is that we kind of inherit robustness from two sources. So we have a framework that allows us to not make this assumption that our model family is true and it can describe the data generating process. And we also use a measure of distance between the data generating process and the model family that is, it has some nice robustness guarantees. So it's also quite robust to model misspecification. So yeah, so we end up with this map. And of course, it's in the similar way, as I said before, because we don't know P star exactly, and we have a posterior distribution. This, again, in the same way, defines a push-forward measure so that we can obtain posterior on theta, which when I say posterior, I don't mean the standard Bayesian posterior. So we don't try to make an approximation of the standard Bayesian posterior. We want to obtain the push-forward measure, which I'm going to explain now how you would actually sample from it. Okay. So the idea is that I can sample from independent samples from the Dirichlet process, which is the posterior, I remind you, is the posterior distribution of the data generating process. And for every independent sample I get, so here, for example, P1, P2, P3, I can map each of these samples to the value of theta that minimizes the MMD between my sample and the parametric model. So here, because the idea is that I don't know P star, I have a whole distribution of a P star here. So the bootstrap comes in because I can bootstrap and sample a lot of times from this posterior distribution. And for each sample I get, that defines a new objective function that's minimizing distance between that particular sample and parametric model. And so by finding these minimizers of the MMD, I get a posterior sample for theta. So ultimately, if I do that a lot of times, it will concentrate that's what I want. I would like it to concentrate around the value of theta that will minimize the MMD between a parametric model family and the true data generating process.
Sample from the Dirichlet prior. So the idea is that it's going to get closer to samples from P star.
Yeah, so that's the Dirichlet process posterior. So that's the posterior distribution of P given the data I have observed. So that's posterior given the data, and I sample essentially around this posterior. So I take samples from the reducible process, which are centered around F prime. So I remind you F prime was, I'll go back. So F prime was the linear combination of my empirical measure and what I have from my prior. So that's where the posterior is centered around. So that's the posterior distribution for P star because I don't know it. And for each sample of the posterior, I get a different theta. So ultimately, I want this to collapse to the infimum of the MMD between P star and P theta. So the idea is that I've set uncertainty on P star because I don't know it, and using that posterior, I want to say something about theta. And pi NPL here denotes, just a reminder, this denotes the NPL posterior and theta. So it's not a Bayesian posterior, so I've put NPL just to differentiate. So this is called, so in the generic case introduced in the papers in the NPL framework, this was called a posterior bootstrap algorithm for a generic loss function. So that's why we just call it the MMD posterior bootstrap for using the MMD. So I talked to you about the approximation of the MMD. So there is also another approximation that you'll actually do in practice, which is approximating samples from the digital process. So that's not exact. I'm not going to go into too much detail on this because I don't think it's super important, but I have some references if you are interested. So usually you would approximate samples through the stick breaking process and use like a truncated sum. And this is an alternative way to do it that was suggested in the NPL papers, which we also use in our method, which comes down to sampling from your prior centering measure. So F was the prior centering measure on the digital process, and these samples, the X tildes will essentially incorporate all the prior beliefs I have, and then you combine the observed data and the prior pseudo data by weighting them through Dirichlet distributed weights, and that's just a bit more efficient than the stick breaking approximation, and that's the approximated sample I get from the Dirichlet process posterior. So here nu hat will just define the approximation of my posterior from now on. So that's what in practice samples P1 and P2 and P3 would look like. And a bit more generically, the algorithm then will be will essentially entail these two steps. So we have the sampling step and the optimization step. The sampling is quite straightforward now, and then admittedly optimization is the trickiest part of the method, as in most of kernel methods, I guess. But the idea here is computationally that every pair of these two steps can be done in parallel. So theta 3 will not use any information from theta 2. It's all done in independent bootstrap samples. Now, in terms of the optimization, so we use gradient-based optimization. In theory, you could use other methods. So the same way MMD has this U statistic, we can have a similar U statistic for the gradient of the MMD. So you could use something like stochastic gradient descent there for actually finding these minimums.
So you have a closed form of gradient?
So if your generator is differentiable, you can either have a closed form depending on the model, or you will have to use auto differentiation. Yeah. Yeah, and I should say now that so the optimization, of course, depends on the choice of kernel. So there is a choice there for the MMD, and it's a hard choice, well-known hard choice, especially because a different kernel will change the objective function completely. It's not that easy to tune that. And even the parameters of the kernel will also affect the optimization objective. So there are some heuristics in the literature that we have used as well. So, I think quite a few people will know here, there's like a median heuristic people use to tune the Gaussian kernel hyperparameter, for example, using median between data. And there's also been other suggestions, for example, using a weighted combination of Gaussian kernels, which is something that we used as well in our experiments. But it is admittedly something that is not, you don't have a guarantee of like which parameter kernel I should use. So that's as part of the optimization process here. Yeah, this is the same algorithm, just a little bit in detail, in case it's easier to follow through. I'll just go very quickly that what we have is observed data. This should be P star, sorry, not P naught, and a prior, which again, if we don't have any expert knowledge and information about P star, then alpha could be set to 0, for example. So that's something quite case dependent. And then the actual algorithm comes down to the 2 parallel steps of sampling and optimizing. And just a quick recap that, as I said, because to optimize the MMD, you need samples from both probability measures and samples from P theta, as we said in the beginning, because that's a simulator-based model we have assumed. It comes down to using the generator function and the base measure U to sample from it. So in practice, that's a bit how it looks like. Okay. Now I think I'll go through theoretical results unless there are any questions now.
So basically, can you go?
Yeah.
So you want to, at each step when you do your optimization to find the theta J, you change the theta, at each step the theta changes and you need to sample new points from P.
Yeah, exactly. So if you use like something like stochastic gradient descent, yeah, you will update theta and then sample again. Sample from the simulator again, yeah. In practice, I use other, but yeah, it's similar, yeah, how it would work.
And is that computation expensive, the fact that you need to sample and compute each time?
Yeah, I mean, if your generator is expensive, obviously it will make that more expensive. But in practice, stochastic gradient descent works quite well. That it ends, like if you use mini batches, it would end up, it would converge quite fast. So if you compare it to something like having to do an accept reject, and you'll have to discard a lot of samples, for example.
But I mean, even once you have a sample, you still need to compute and you need to recompute it at every step.
The gradient, yeah, you would use automatic differentiation. Yeah, so you would, yeah, you need to compute something. Yes, you're right. So you'll probably use a gradient and then update your theta. You wouldn't compute the MMD exactly necessarily, but yeah, the gradient you will have to. Yeah, yeah. Okay, so theoretical results. So for all of the results we have, so the main assumption, so I talked about the IID assumption at the beginning. That's mainly due to the fact that we use a conjugate posterior for the Dirichlet process. So it doesn't really come into the proofs for this MMD generalization bounds, but if we want to use that non-parametric prior, you kind of need that inherently. The other big assumption we make is that the kernel is bounded, which, yeah, is quite a common one in quite a lot of cases in order to prove this generalization bounds. And without loss of generality here, I've just assumed the bound to be 1. So in terms of generalization error, what we care about is the expected error we expect to see in terms of the MMD, between the true data generating process and this P theta defined through the map theta star. So theta star again is the map that minimizes the MMD between P and P in the model family. So that's why we have a double expectation here. So we have expectation in terms of the finite sample we have from P star, and also expectation because P is now a random sample from the posterior of P star. So nu hat is the approximated posterior of the directional process. And this also holds for the exact, not just the approximation, but I think the approximation is probably more interesting because it's what we use in practice. And this, of course, is trivially lower bounded. So if you're, so going back to the plot we had at the beginning, if our model is in fact unspecified and P star is not a member of the model family, then there is a best case scenario we can have here in terms of the MMD. So that's where we would like. So we would like, if we have a lot of data as the data size grows, for the error to kind of go towards this value here, the best case. So this difference, the generalization error, so we showed is upper bounded by these two terms. So here the overall rate of this is 1 over square root of n, which agrees with other similar results for MMD estimators in the literature. So we kind of recovered that. And here just the lower round alpha comes from the directional process. But the overall rate of this term is 1 over n. So this is the dominated term. And now we can actually use this result to show something in terms of posterior consistency of the posterior we have in theta. Just taking a step back here. So if we had a standard Bayesian posterior, so if we had a posterior that was actually directly on theta, what a posterior consistent result would look like would be that I would like, as I get more and more data, and this value goes to 0 here, I want my posterior on theta to go to 0 for values of theta that induce large MMD values, right? So what this says is just that the posterior will concentrate in increasingly small and small neighborhoods around this thetas that induce the infimum of this MMD. But we don't actually have a posterior in theta directly. So we only have it indirectly through the posterior in P star and the push forward measure. So we just showed a similar result, which is that, which concerns the posterior on P star. So it's exactly the same that we want the posterior on P star to concentrate in increasingly small and small neighborhoods that induce values of theta, but give you small MMD values. So essentially, again, concentrating around this infimum, so thetas that give this infimum MMD. And I should also mention, I didn't mention that earlier, that of course this 0 if we have a well-specified case, and in the MMD ideally you would like your kernel to be characteristic so that you can actually recover the true model if we have a well-specified case. So it's not needed specifically, but it's what you would actually want in practice for this to actually be a metric. And finally, we just considered a specific case of misspecification, both because it's seen quite a lot in real life. It's the Huber's contamination model, so the presence of outliers in the data set. And also because we used quite a few of these examples in our application section, because it's quite easier, you know what your target is, so it's easy to assess if you're actually finding good values of theta. So the result is similar to the first generalization bout, but now I care about if my data comes from, if a small proportion of the data, comes from a distribution Q, I care now about the MMD between P tilde and P theta, and P theta, a model family. So I would like now my expected error in terms of P tilde, again, to concentrate around where I want it, to the infimum. And what this bound says is essentially the same. It just has the extra term of the contamination, and it just gives you a guarantee that if your contamination level is not that large that it will dominate this 1 over square root of n term, then no matter what Q is, no matter how far away a different Q is, then you would still obtain the same rate you had in the generic case. Yeah, let's move on to a few applications. So first thing we considered was a G-and-k distribution, which is used in likelihood for inference literature a lot. So it's a simulator-based model. We don't have the form of the likelihood. I haven't included it here, but for simplicity. But this is what the data looks like from a G-and-k. So we considered a contaminated model. So a small proportion of the data would actually come from a shifted distribution, so just setting some outliers on the right and the left. So this is just a very small illustration to show you what we would like. So essentially what we aim for is if we make an estimate for theta and we will sample from the G-and-k again, we would like the data to not be as sensitive to these outliers as we can be. So an example, one of the methods we compared against was an ABC-based method using the Robustness time distance. There are a few more in the paper as well. So we obtained an estimate for theta for after 500 posterior samples. We just took a mean estimate and just generated some new data. So here blue is the original data, and then orange is some new generated data, just to show a bit how the sensitivity to outliers. And then there's using again 500 samples from this bootstrap method. You see a bit how you would like this to not concentrate, but mimic the way the data performs from p theta naught. And just to see this a little bit better, so we have posterior marginal densities for each of the 4 parameters. So here we perform inference for the 4 parameters of the G-and-k distribution, and we produce around 500 samples from each method. And here we see both the bivariate posterior densities and the univariate ones. And the dotted lines indicate where the true parameter values lie, so the target. And from left to right, we see an increasing level of contamination. So this is the posterior densities, so around where we would like it to concentrate. And I think the intuition from this is that because this non-parametric learning framework and the posterior bootstrap it doesn't try to approximate the standard Bayesian posterior in the absence of the likelihood, but instead it just tries to target this infimum of the MMD, so tries to get as close as possible to P star. So it's more successful in ignoring outliers essentially. Rather than a method that would try to approximate the standard Bayesian posterior, so inherently will be more prone to outliers. And yeah, obviously it's not perfect. So you can see, if I have a lot of bootstrap samples, I will potentially have some that are a bit further away, but you would like it at least to get a concentration around where you would like. So another example, maybe a little bit more interesting, is what's called the toggle switch model. So that's used in biology because it tries to explain how a few particular genes interact over time. So that's the generator, just to convince you that it's a simulator-based model and you don't have a likelihood function. So this has 7 parameters. It's still the output is still 1-dimensional, but the latent dimension is something of the order of 600. So usually T here, in order to have something that has stabilized, is around 300 in practice. So for example, what you asked earlier, it's like, yeah, of course, this generator will be more expensive. So the optimization will also be a bit more computationally expensive to do. And again, so we want to, again, produce some posterior, the posterior sample for theta. So we added some Cauchy noise to 10% of the data. And we show here, so the data looks like on the bottom right panel, it's like a bimodal thing after it has stabilized. And again, here we have the same sort of plot, the posterior densities and the dotted lines indicating for its parameter around where is the true parameter value. And yeah, and so I guess here in terms of the optimization, I think I mentioned earlier, so we used a weighted combination of Gaussian kernels, linear combination of Gaussian kernels. So it was definitely more challenging. So I would say like something I would look further for this method would be potentially if you could find some guarantees or something a bit more theoretical grounded on like how to choose this kernel to make something like that an objective more potentially convex, or have some sort of idea that this will definitely converge and get a good minimum. So that's the biggest challenge, which is, I mean, not specific to this, but I guess more generally in kernel methods and using MMD estimators. And in real life, I would say that you would like to have some application as well, that it's not just a contamination, but it's completely misspecified. So we have some toy examples that we did that, but it's harder because you wouldn't be able to assess it. You wouldn't know where this infimum of the MMD actually is. So yeah, in real life, you would want this, you want to check that as well. But that's just a bit of an illustration to get an idea how it would work. And I think with that, I'm done. So thank you very much for listening. And yeah, let me know if any more questions. Happy to chat.